Now let me show you another example of control variable. This is actually a different example. This example is a popular empirical strategy called regression discontinuity design, or RDD. RDD is usually not presented as a control variable approach. However, it can nevertheless be understood as a method to satisfy our conditional random assignment assumption. Let's see how it works. So RDD is used to estimate the effect of a dummy random variable D. So that's our causal variable X, okay? Because now it's a dummy variable, we call it D. To estimate the effect of D on an outcome variable Y. So our causal model is Y equals beta 0 plus beta 1D plus U, where D is the causal dummy variable and U can be understood as the potential untreated outcome if you set up the causal model using the potential outcome framework. Or it could be contributions of all other factors other than D that contributes to Y. The key for RDD is to have a continuous random variable W called the running variable. And this running variable is important because it crossing a threshold should be important for the determination of D, for the value of D. If W crossing a threshold completely determines D, perfectly determines the value of D, or in other words, if D is an indicator function of W crossing or not crossing a threshold for some threshold value little w 0. Then we say we have a sharp regression discontinuity design. So D is sharply determined by W crossing the threshold. If the relationship between D and W is not that sharp, if W crossing the threshold doesn't completely determine the value of D, but only makes D equals 1 more likely, then we say we have a fuzzy regression discontinuity design. We will talk about the fuzzy regression discontinuity design toward the end of the semester. Today, we'll just talk about sharp RDD. In fact, sharp RDD in practice is pretty rare, but let's consider this perfect example from actually my undergrad university. This is actually a true story. So my undergrad university put great emphasis on physical education. It had an infamous boot camp coached by a PE teacher nicknamed the Devil. So the boot camp is a physical training class that is very, very demanding. How are students assigned to this bootcamp? This bootcamp is according to an evaluation test that every student takes in the freshman year. If the student's score is less than a threshold, then the student was mandated to train in the bootcamp for the entire sophomore year. The students who scored above the threshold were allowed to sign up for the bootcamp, but as a matter of fact, nobody actually did. So no one scored above the threshold joined the bootcamp, and all of the students who scored below the threshold were mandated to join the bootcamp. So if D is having trained in the bootcamp, then D is perfectly, completely determined by the running variable W, which is the evaluation test score in the freshman year. And this W0 is the threshold set by the university. So that is a very clean, very perfect sharp RDD design example. Now, suppose that we want to use this RDD to study the effect of the boot camp on BMI, body mass index, at age 40 using the causal model, using this simple causal model. Because we have a sharp RDD, D is completely determined by W, so D is 1 if W is less than this threshold, and D equals 0 if W is greater than or equal to this threshold. Because D is deterministic, once W is given, we have EU given DW equals EU given W. Now, this is key. This is very important. Why is this true now? This is true because D is a deterministic, a non-random function of W. Once W is given, D is either 1 or 0. D is no longer random. Therefore, we do not need to condition on D anymore once W is given. So D can actually drop out of this conditioning. So EU given DW equals EU given W. The reason is the information contained in W nests the information contained in D. Okay, we do not need to condition on D once we already condition on W. So because of the definition of D, this conditional random assignment assumption for D is mechanically automatically satisfied, which is great because that means we can then turn this causal model with an endogenous D into a conditional mean model of Y given D and W. So now if we take conditional expectation of Y given DW, then that actually equals conditional mean of Y given W because the information contained in D is nested in the information contained in W. And EY given W equals beta 0 plus beta 1D plus EU given W. So this is simply applying this conditional expectation on the right-hand side, and this will be what you get, right? Knowing that D is a non-random function of W. All right, now let's make the simplifying assumption that EU given W is linear in W. If we make that simplifying assumption, then EY given DW will be, remember that is beta 0 plus beta 1D plus EU given W. And EU given W is gamma 0 plus gamma 1W. Then you plug that in here, and you're going to get beta 0 plus gamma 0 plus beta 1D plus gamma 1W. So we have obtained a linear conditional mean model. If this linearity simplifying assumption is satisfied, then this linear conditional mean model is correctly specified, in which case running an OLS regression of Y on D and W will give us a consistent estimator for beta 1. So this is the simplest version of the sharp RDD. Okay, this is the simplest version of using sharp RDD to estimate the causal effect of D. But of course, can you justify this linearity assumption? Is U really related to W in a linear way? Maybe not. So this linearity assumption may be wrong. However, it can be relaxed. It can be relaxed by adding nonlinear terms like we did before, it can be relaxed as long as we maintain that EU given W is continuous at W. If it is continuous in W, then we can derive that beta, I think beta 1, we used the beta 1. So beta 1 will be the difference between this left limit of EY given W equals little w and the right limit of that. So why so? That's because EY given W equals little w equals beta 0 plus beta 1, 1 W greater than or equal to W0 plus EU given W equals little w. And that equals beta 0 plus, let's say this is G of little w. Beta 0 plus G of little w for W, sorry, this should be less. For W greater than or equal to little w0, and this equals beta 0 plus beta 1 plus G of W for W less than W0. And when you take the left limit, then you're taking the limit of this function as W approaches W0. So that left limit equals beta 0 plus beta 1 G of W0. Notice that we maintain the assumption that G of W is continuous. And this right limit, on the other hand, equals the limit of this expression when you take W to W0 from the right. So that should be beta 0 plus, that's plus G of W0. So the difference between these two limits is exactly beta 1, the causal effect we are interested in. And because of this, because beta equals this limit value of the conditional expectation of y given W on the left side of W0 and the limit of this same function on the right side of the conditional expectation of y. Notice that because of this, because beta is the difference, beta 1 is the difference of these two limits, the shape of EY given W equals y, the shape of this function of W only matters for W close to W0. For W that's not close to W0, those points or the value of EY given W equal little w at those points not close to W0 do not have any effect, right? Do not affect the limits at all. So only the shape of this conditional expectation function close to W0 value matters for estimating beta 1. So therefore, for the RDD estimator, when we want to relax the linearity assumption, we actually typically do not relax the linearity assumption by adding polynomial or other nonlinear terms of W into the regression. Those, in theoretically speaking, work. However, they do not work so well in finite samples. Instead, we focus attention on a subset of data with W being in a small interval around the threshold value, W0. So this makes sense because beta 1 is determined by the shape of this function only around the threshold value. So we're going to focus on a subset of data where W is in this small interval around the threshold. And the width of the interval is called the bandwidth, which is a positive number that you can choose. And once we focus on this small interval, we can run a local linear regression, which is basically an OLS regression using data that satisfies this restriction, using only the data points with W that is in this little interval. And that way, this OLS regression estimator of Y on D and W, when you restrict attention to this subsample, will give us the RDD estimator for the causal effect, which does not require the linearity assumption for EU given W. Instead, you simply use the command regress Y on D and W if W satisfies these inequalities. And notice that we always use the comma R so that we produce the robust standard error. So you can regress Y on D and the control variable on this small interval. And the assumption here is that on this small interval, EU given W is close to being linear. And that is typically reasonable because if EU given W is a smooth function, let's say suppose EU given W is something like this. And suppose we are, the threshold is here, suppose that is W0, then overall this EU given W is not linear. However, if you restrict your attention to a small interval around this little W, 0, the threshold, then on this little interval, this curve EU given W equals little w isn't too different from linear. If you draw a linear function closest to it, it doesn't seem that the linear function is so different from the curve when you restrict your attention to a small interval around the threshold. So that is why you can still use linear regression, linear OLS regression, if you would restrict your attention to a small interval around the threshold. Okay. So that's how you relax the linearity assumption on this function in RDD. Of course, there is the question of how to choose the bandwidth, how to choose the small interval. Typically, that can be chosen by cross-validation. However, the implementation of cross-validation is kind of tedious in Stata. So if you can't do that, one thing that you can do is to try a bunch of bandwidth values and find a range in which your estimate seems to be stable. Okay. Typically, you can do that. Just to one thing to make sure is that your subsample, the subsample that satisfies this restriction, you want to make sure that it's not too big. You want to make sure that it's not too small. Say not smaller than 20 observations, and because if it's too small, then this regression will be using too few observations. The estimates will not be accurate. But of course, you don't want H to be too big either, because when H is too big, the linearity on that interval will not be a very good approximation. right? So you kind of start from an interval that includes, say, 15 or 20 observations, and then increase it from there and see how your estimate for the causal effect changes. Hopefully, it's stable for a range of age. Then you can have a good idea of what the causal effect is. In practice, here is a little bit more details about RDD with local linear regression. In practice, for whatever reason, it is customary to allow different slopes for EU given W. In other words, it's customary to allow EU given W to have a kink at W0. So EU given W, maybe it's not like this. Maybe it's kind of, it's got a kink somewhere in the threshold value. Why do people want to allow this kink? There are different reasons, but it's not necessary to allow this kink, but usually people still do. So you can allow this kink by adding the interaction term of D times W minus W0 to this local linear regression. Notice that you want to include the interaction or the product between D and W minus W0, because if you don't subtract W0 from this interaction term, then the coefficient on D will not be the estimate for the causal effect. But if you do subtract W0 from W, then you can still take the coefficient on D as the estimate for the causal effect beta 1. So that is sharp RDD, how you do it in Stata. Now let's discuss the assumptions made for the RDD. Notice that the continuity assumption for EU given W, that little GW function, that continuity assumption is indispensable. It's key for regression discontinuity design. What that means is we want only the treatment to jump when W across the threshold W0. We do not want any other factors contributing to Y to jump at that point. The reason is simple. If there are other factors in U that also jump at W0 point, then EU given W, for example, may be written as a function of the indicator plus a continuous function of W. Let's say linear function of W. In that case, EY given DW may be written as gamma 0 plus beta D plus gamma 1, this indicator plus a linear function of W. Now, because this is a sharp RDD, D is completely determined by W crossing the threshold, so D equals this indicator. When D equals this indicator, clearly this model has perfect multicollinearity problem. You are not able to estimate beta 1 separately from gamma 1. So that gives you a problem. If you mechanically apply the RDD, not ignoring this term, then your RDD estimator will actually estimate the combination of beta 1 and gamma 1. And that combination, you cannot separate beta 1 from this combination. Okay. So RDD will not consistently estimate the causal effect if your error term, expectation of the error term given W is not continuous at the threshold. Now, Is the continuity assumption reasonable for the bootcamp example we discussed? It perhaps is. We can think about what the error terms are. So remember, our Y is the BMI at age 40. That's 20 years after graduation, after the bootcamp. And D is the bootcamp. And W is score from the freshman year. Okay, so the PE score from the freshman year. So what are the other factors that contribute to BMI rather than besides the bootcamp? You might imagine maybe your habit, life habit, or genetics, or all of those things, right? So genetics is probably continuous in score. It's not even related to score. And maybe your innate habit of whether you like to exercise or not, suppose that is not affected by the score, or maybe it was affected by the score, but in a continuous way, then the continuity assumption is still satisfied. But you can also imagine some story in which the continuity assumption is not satisfied. For example, maybe failing the evaluation test was a wake-up call that motivated a permanent lifestyle change. If that happened, regardless of the boot camp, failing the evaluation test would have had a discontinuous effect on your BMI at age 40. So that will create a discontinuity in EU given W, and it will violate the continuity assumption. Or another story in which EU given W might be discontinuous, might be this, might be the students who barely passed or different in some way than the students who barely failed. So they almost have the same score, but the students who barely passed are different than the ones who barely failed. It could be because the students who barely passed were the ones who were really, really scared of exercising. And the one who barely failed were kind of indifferent. If that is the case, then these two groups of people will have very, very similar W around W0, but they're different. So their aversion to exercise, which is part of U, are different, even though their W is very close. So if that is the case, then EU given W also has a discontinuity at W0. And that will create problem for identifying the causal effect of the bootcamp. All right, so that's the end of this video.